Welcome to the world of C++ performance optimization. In this video, we're going to explore techniques for writing efficient C++ code. We will cover memory management, algorithm optimization, and how to leverage modern C++ features to boost your application's performance. Let's dive in. Let's begin with memory management fundamentals. The first key principle is to minimize heap allocations. Heap allocations are generally slower than stack allocations, so it's best to avoid them when possible. Next, prefer stack allocation when possible. Data stored on the stack is managed automatically and is much faster to access. Employ smart pointers to prevent memory leaks. Smart pointers automatically handle the allocation and deallocation of memory, preventing common memory errors. Consider custom allocators for specialized needs. Custom allocators can be tailored to specific memory usage patterns, optimizing performance. Finally, reduce memory fragmentation. Fragmentation can lead to inefficient memory usage and slower performance. On the left, we have an example of bad code that uses multiple heap allocations inside a loop, which can be very slow. On the right, we have better code that uses a single stack allocation, which is much faster. This is because stack allocation happens during compile time. Now, let's talk about smart pointers for memory management. There are several types of smart pointers available in modern C++, and they can greatly simplify memory management and prevent memory leaks. The first one is STD, unique_PTR, which provides exclusive ownership of a resource. Only one unique_PTR can point to a given object at a time. Then STD, shared_PTR, which allows shared ownership with reference counting. Multiple shared_PTR instances can point to the same object, and the object is automatically deleted when the last shared_PTR is destroyed. Finally, there is STD, weak_PTR, a non-owning reference to a shared object. It's used to observe an object managed by shared_PTR without participating in the ownership. As a general rule, you should avoid raw pointers for ownership to prevent memory leaks. It's better to use make_unique and make_shared factory functions to create smart pointers. They provide exception safety and can be more efficient. This prevents memory leaks. In the given code, we use STD, make_unique to create a unique_PTR and STD, make_shared to create a shared_PTR. This makes resource management automatic and safe. Let's discuss move semantics and perfect forwarding. Move semantics is all about avoiding unnecessary copies. Move semantics allow you to transfer ownership of resources from one object to another, rather than making a deep copy. You should implement move constructors and move assignment operators for your classes. These special member functions allow you to efficiently move resources. Use STD, move for value conversion. STD, move casts an object to an value reference, enabling the move constructor or move assignment operator to be called. Perfect forwarding allows you to forward function arguments to another function without changing their type. STD, forward is used to perfectly forward arguments. Move semantics and perfect forwarding can significantly reduce memory operations, leading to improved performance. In the given code example, we have a data buffer class with a move constructor and move assignment operator. These functions use STD, move to transfer ownership of the data vector, rather than making a copy. It is very helpful when there is dynamic memory allocation. Let's explore compiler optimizations. Compilers are powerful tools that can perform various optimizations to improve the performance of your code. To enable compiler optimizations, use optimization flags such as O2 or O3. These flags tell the compiler to perform various optimizations, such as inlining, loop unrolling, and dead code elimination. Enable link time optimization or LTO. LTO allows the compiler to optimize across multiple files, potentially leading to significant performance improvements. Profile-Guided Optimization, or PGO, uses runtime profiling data to guide the compiler's optimizations. This can result in code that is better tailored to the actual usage patterns. Use constexpr for compile time evaluation. Constexpr allows you to perform computations at compile time, which can improve performance by avoiding runtime overhead. Understand inlining with the inline keyword. Inlining replaces a function call with the body of the function, which can improve performance by avoiding function call overhead. You can also use __ force inline to strongly suggest inlining to the compiler. In the code example, we use constexpr to compute the factorial of a number at compile time. The inline keyword tells the compiler to try to expand the square function at the point of call. Let's consider data structures and algorithms. The choice of data structure and algorithm can have a significant impact on performance. Choosing the right container for the job is crucial. Use std. Vector when you need contiguous memory and fast iteration. Std. Unordered _map provides on average O1 lookups, while std. Map provides O log n lookups. So prefer std. Unordered _map when you need fast lookups and don't need the elements to be sorted. When using std. Vector, reserve capacity to avoid reallocations. Reallocations can be expensive, so it's best to avoid them when possible. Also, consider custom data structures for specific needs. Sometimes the standard data structures may not be the best fit for your specific problem, so consider creating your own. Remember to measure performance. Don't assume that one data structure or algorithm is always faster than another. Always measure the performance of your code to see what works best in your specific situation. In the given code, the optimized version pre-allocates memory using the reserve function to avoid multiple reallocations, improving performance. Let's optimize function parameters. How you pass parameters to functions can impact performance. When passing large objects, pass by const reference. This avoids making a copy of the object, which can be expensive. Pass by value for small types, such as integers or booleans. For very small types like less than or equal to 2 words, passing by value is usually faster because it avoids the overhead of indirection. Use value references for move semantics. This allows you to efficiently transfer ownership of resources. Consider return value optimization, or RVO. RVO allows the compiler to avoid making a copy of the returned object. Use universal references with templates. Universal references can accept both value and revalue references, providing flexibility and efficiency. In the code, we have different versions of the process data function that take parameters by value by const reference and by revalue reference. The version that takes a parameter by const reference is usually the most efficient for large objects that don't need to be modified. The version that takes a parameter by revalue reference can be used to efficiently transfer ownership of resources. Now let's talk about cache optimization. Optimizing for CPU cache can greatly improve performance. Optimize for cache locality. Access data in a way that maximizes cache hits. Use contiguous memory structures. Contiguous memory structures, such as arrays and vectors, tend to have better cache locality than non-contiguous structures, such as linked lists. Align data to cache lines, which are typically 64 bytes. Aligning data to cache lines can improve performance by ensuring that data is loaded into the cache in a way that minimizes cache misses. Avoid cache thrashing with large strides. Cache thrashing occurs when data is accessed in a way that causes the cache to repeatedly load and evict data. Finally, consider data-oriented design. Data-oriented design is a programming paradigm that focuses on organizing data in a way that is efficient for the CPU cache. In the given code, the cache-friendly version iterates through the matrix in row major order, which maximizes cache hits. The cache-unfriendly version iterates through the matrix in column major order, which results in more cache misses. Let's discuss multithreading optimization. Multithreading allows you to execute multiple tasks concurrently, which can improve performance on multi-core processors. Use STD thread for basic threading. STD thread provides a simple way to create and manage threads. Consider thread pools for task management. Thread pools can improve performance by reusing threads, which avoids the overhead of creating and destroying threads for each task. Leverage STD async for simpler parallelism. STD async provides a high-level interface for launching asynchronous tasks. Beware of false sharing and data races. False sharing occurs when threads access different data items that are located in the same cache line. Data races occur when multiple threads access the same data item without proper synchronization. In the code, the parallel process function divides the data into chunks and processes each chunk in a separate thread. To summarize, in memory optimization, use smart pointers for automatic memory management, prefer stack allocation over heap when possible, and leverage move semantics to avoid unnecessary copies. For algorithms and data structures, choose appropriate containers for your use case, optimize for cache locality and memory access patterns, and pre-allocate memory to avoid reallocations. In compiler optimizations, use appropriate optimization flags, leverage constexpr for compile time computation, and consider profile-guided optimization for critical code. Finally, in concurrency, parallelize independent operations, be mindful of synchronization costs, and avoid data races and false sharing. Remember to measure first and optimize second. Always profile your code to identify actual bottlenecks before applying optimizations. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.